Okay, step functions and their utility to solve linear ODEs, where the forcing term is a piecewise defined function. So last time we introduced step function or Heaviside function, and we worked out some examples, and we turned a piecewise defined function in terms of sum and products of step functions, so we can use Laplace transform on them, so we can solve linear ODEs. So today we're going to do two things. One, we're going to prove this equation. We couldn't get to it last time. This is what's going to help me solve those type of ODEs without having to resort to integrals, and then I'm going to work out an example from start to end. Okay, so let's begin with this proof. And by the way, this one sometimes you see this one in books, and they are identical. It's almost like first name, last name. They don't look the same, but they are referring to the same person. So in other words, if you let t here be t minus c, these are the same. If you let t be t minus c, then this becomes t minus c plus c, which is g of t, okay? And as you know, Laplace of g of t is capital G of s, definition of Laplace transform. Laplace of little f of t is capital F of s. So these are identical. If we prove this, then you get this for free, because you just replace t by t minus c in this proof, and it'll pop up, okay? So I am going to begin with the left-hand side of the equation, okay? And the definition of Laplace of this function here, this is a function. I know it's a product of two functions. Nonetheless, it is a function. So it's the integral from 0 to infinity, e to negative st, and then this piece, okay? Now, recall h of t minus c, when we introduced this type of functions, it looks like this, okay? Go back to the last video to see simple example, h of t minus 3, h of t minus c, and h of t minus c minus h of t minus d, right? So look them up again. So this function, by definition, is 0 when t is less than c. Sometimes since t is a time, this means this really. And it's 1 when t is more than c. So that critical value was c, if you recall, okay? So if that is the case, what I'm going to do is, this is a very similar proof to something we did last time. We're going to break this integral from 0 to c and then c to infinity. That's the same thing as going from 0 to infinity. And the reason we break it that way is so we can take advantage of this. So from 0 to c, t is from 0 to c. That means t is less than c. That means this piece here is 0, which makes this entire part 0. And then we add the same integrand, right, from c to infinity. Now, t varies from c to infinity, which means t is more than c. So therefore, h of t minus c has to be 1. So the leftover of that entire left-hand side is just the integral from c to infinity, e to negative st g of t dt. That's what I wrote here, okay? Now, this is not a Laplace. You cannot call this Laplace of g of t, even though you have an e to negative st g of t, because you're supposed to start with 0. So we're gonna let this is starting with c. So we're gonna let capital T be t minus c, because if t equals c here, that means t minus c is 0, and that's what I want. So we're gonna let capital T be t minus c. That's my change of variable, which means the little t is capital T plus c, and that also means that little dt is d capital T. So we make the change. This gives me capital T equals 0. Capital T goes to infinity when little t goes to infinity, because one is just the difference between the two of them is just a constant. And this one becomes g of c plus capital T. Little dt becomes d capital T. And this little t here becomes c plus capital T. So we got an extra piece here. So I'm going to split this. This is e to the negative cs times, not plus, but times e to the negative st. Now, e to the negative cs does not depend on t, so I took it out. So you're left with 0 to infinity, e to the negative st, g of t plus c dt. Now, you notice I went back to little t. Okay, I just hate this capital T. This doesn't mean that this t is the old t, okay? It's just another dummy variable. So this is a dummy variable. I changed it back to a little t, okay? So this is the little t equals 0 to little t approaching infinity. Okay? Now, for sure, this is a Laplace because you're going from 0 to infinity, e to negative st some function. So that is Laplace of g of t plus c. But don't forget this factor, okay? And that is exactly what I'm trying to prove here, okay? So this is going to be extremely useful for us, as you will see in a minute. So here is our example. So this is the very first time I give you an ODE where the forcing function is not the typical exponential, binomial, sine, cosine, or even secant, cotangent, where we had to use the Wronskian, if you recall, because in the past we have worked with ODEs where the coefficients, like the 5 here and the 6 and the R of t, were continuous, and sometimes they were differentiable. Well, now this time this forcing function is a piecewise defined function. And we're going to write it in terms of Heaviside functions, kind of a built-in block. So we're going to write it as a sum and product of step functions or unit steps. So you may remember this one. That was the one I gave you for homework. So I chose it so that we can confirm to see if you got it right. Okay? So how do you solve this type of linear ODEs? Remember, this equals that. Okay? Now, before I get started here, we know we're going to use Laplace. And Laplace transform will never work for you if you don't have an initial condition. Or I should say initial conditions in this case, because I have y double prime. Which means if you have a linear ODE, you're not going to be able to use Laplace transform. But if you have an initial value problem, you will be able to use Laplace. And I will explain to you why in a second. So we're going to write R of t as the sum and product of unit steps, okay? So basically, let's start with this one first so I don't confuse you, okay? So the way you write this piece, if you remember, was it's h of t minus 0, which is h of t, minus h of t minus 3, the whole thing times 2. That's what I wrote here. There is a 0 here, t minus 0, okay? The third piece is h of t minus 3 minus h of quantity t minus 8, the whole thing times 4, okay? And then the last one is just h of t minus 8 times negative 1. Now the first one, you know, you might think, let's say t can be negative. In other words, we're saying t is less than 0. So t goes from negative infinity to 0. So you may want to think of, oh, could it be something like h of t minus infinity minus h of t minus 0, right? You may want to think about, why is it, what should I write here that I would have to multiply by this function 0? This is the function 0, of course. You have to multiply by the functions, whatever is given to you, like negative 1, 4, and 2. I just wrote blah because I don't care what it is, because I know I'm going to hit it with 0. But you really want to think about how do you express this in terms of h, okay? Now, if t is definitely greater or equal to 0, that means t equals 0 here. Because if you have to be less or equal to 0, and you have to be greater or equal to 0, that means t equals 0. So how do you write that in terms of h? You want to think about that a little bit. Anyway, so once I rewrite it like this, then I'm going to apply Laplace transform on the left-hand side and Laplace transform on the right-hand side, which is this piece here. Now, I noticed on the homework, some of you decided to apply Laplace transform too fast, like on this one. You're wasting time, okay? You want to clean up this mess first. So that's 0, it's gone. And you have twice h of t. And then you have negative 2h of t minus 3 plus 4h of t minus 3. That gives me twice h of t minus 3. And then we have negative 4h of t minus 8 minus another h of t minus 8, which is negative 5h of t minus 8. So you want to really clean up this mess, make it look like this first, before you apply Laplace transform on the left-hand side and the right-hand side, okay? It's almost like moving. You want to clean up the clutter before you move. You don't move, then you throw stuff in the trash. You want to clean things up first, then you apply Laplace transform, okay? So what I'm going to do next is I'm going to find Laplace on the left-hand side, which is going to take me a little bit of time. And then I'm going to apply Laplace transform on the right-hand side, which is this piece, which will also take me some time. So I'm going to work with them separately. I'm going to just focus on the left. When I finish, I'm going to go to the right, and then I'm going to make them equal and try to solve for my function. Remember what we're looking for. We're looking for y of t. This is the question. Never lose sight of what you're looking for. You know, have you ever been in a situation where you start debating someone and arguing, and then 2 hours later, you just want to win the arguments. You don't even know what you're arguing about, right? So don't lose sight of what we're looking for. We're trying to solve for y. We're applying Laplace transform on both sides. Hopefully Laplace of y will pop up. And once that pops up, then we can use inverse Laplace on Laplace of y to get the y. Okay? So I'm going to focus on the left-hand side. Now, Laplace of this is a linear, right? As you know. So it's Laplace of this plus 5 times Laplace of that plus 6 times Laplace of y. Now, we learned a few properties about Laplace of the nth derivative, and it was a really long equation if you remember. But Laplace of y double prime, if you remember, is s squared Laplace of y minus s f of 0 or y of 0, this one, minus y prime of 0. This should remind you why Laplace cannot be used if you don't have an initial value. Because if you only have the ODE and you apply Laplace, you're going to be stuck right there. Because this Laplace of y double prime depends on the initial conditions. And Laplace of y prime depends on this initial condition. That's why we need an initial value problem, okay? Let me erase this dot here. Here you go. So this piece here is these three terms. Okay, I put them in parentheses for you. Plus 5, and then Laplace of y prime is s L of y minus y of 0. And that just goes down there, okay? So I'm going to clean this up. This is 0. This is 0 times s. It's gone. And this is 0. So you'll end up with s squared Laplace of y plus 5s Laplace of y plus 6 Laplace of y. That is the left-hand side. Okay, this left-hand side, okay? That is exactly what I wrote here. And, of course, I'm going to factor out Laplace of y. I got s squared plus 5s plus 6. Now, I want to pause here before I go to the right-hand side. I want to make a point to you. I deliberately picked this piece of the ODE to be factorable, think of x squared plus 5x plus 6. It's like x plus 2 times x plus 3. Now, of course, I got s squared plus 5s plus 6, right? It's kind of expected. But be careful. Don't assume that if you replace this by s squared and this by s and this by nothing, you just get a 6 like here. It should always work. It will always work if y of 0 and y prime of 0 are both 0. You wonder why I picked them, because I'm lazy. I want to have easy initial conditions. If they were not 0, I wouldn't know what to get here. I might get something else, of course. And I also did this to see if I am correct, because sometimes I make careless errors. So now I know for a fact that so far up to here, I'm correct. Okay, I make a lot of algebraic errors, so bear with me and watch what I do. And if you see errors, point them out to me. Okay, so that's the left-hand side. Now we're going to go to the right-hand side. We want to find Laplace of this quantity. Okay, so Laplace of that quantity, again, Laplace is linear, a linear operator. So you get this, pull the 2 out, pull the 2 out, pull the negative 5 out, you get this. And now you see the significance of the thing we proved earlier. Without this or that, because they're the same, without this, I'll be completely stuck here. I wouldn't know what to do. I know these are step functions, but how do you take Laplace? I wouldn't know what to do. So, remember what we proved. So we're going to use it. So the 2 remains, okay? I'm trying to find Laplace of h of t. That means c is 0 and g of t is 1. Okay? According to this, c must be 0 and g of t equals 1. What does that mean? The right-hand side has to be e to the negative 0s Laplace of 1. Remember, if g of t is 1, g of any input has to be 1. G of t is a constant function. So no matter what the input is, that is 1. And that's why I wrote twice, the 2 came from here, e to the negative 0s Laplace of 1. Next piece, the 2 remains. C here now is 3. And g of t is still 1. So I'm still going to get Laplace of 1. Again and again and again. Okay, that's not a surprise. That should give me twice e to the negative 3c. Okay, Laplace of 1. And the last one is negative 5. E to the negative 8c, because 8 is c. Negative 8c, Laplace of 1 again. Okay, now you know that Laplace of 1 is 1 over s. Don't forget those simple ones. Laplace of 1 is 1 over s. And if you have inverse Laplace of 1 over s, you should get 1. Okay, we're going to use this in a minute. Okay. So that's 1 over s times this. This is 1. So you get 2 over s plus 2 times e to the negative 3s over s minus 5 e to the negative 8s over s. Okay? By the way, anytime you see exponential to some negative exponents, you know you have a discontinuous function. Just keep that in the back of your head. So usually we get really nice numbers, but now the moment you start getting e to some negative s, you know that this has to be discontinuous. Okay, so here are we. Where are we? We are here. So that's the Laplace of the right-hand side. And Laplace of the left-hand side is this. So we're going to force this to be that. Right? Of course, I'm looking for y, which means I want to isolate Laplace of y. So I'm going to divide by this piece. That's all I did here. So you take this, and divide it by that. Okay? Now, I just dragged the s to the bottom to keep it simple. And I also factored s squared plus 5s plus 6. I wanted nice numbers. Okay? Now you know what you're going to do. Before you apply inverse Laplace to find y, this is a nightmare unless you use partial fractions. And partial fractions by themselves will take you a long time, okay? But last time I showed you a nice trick, didn't I? So we want to take advantage of that trick, okay? Here it is. So we're going to write this as a over s plus b over the other factor plus c over the third factor. And we're not going to cross multiply and solve systems of equations. We're going to play the trick we did last time or 2 videos ago. In order to find a, you go back here, you ignore s completely and plug in 0 for the rest. So it's going to be 2 plus 2 e to the negative 3 times 0 minus 5 e to the negative 8 times 0 over 0 plus 2 times 0 plus 3. That's all I did here. And I got negative 1/6. I hope I didn't make a mistake. To get the b, we're going to go back here and we're going to replace s by negative 2 here and here and here and here and ignore this factor. I hope I am correct. That's what I got. So that's all I did. And for c, you're going to plug in negative 3 here and here and here and here and ignore this factor. And I got this ugly quantity. So A looks simple, B looks bad, and C looks even worse. So Laplace of y has to be A over S plus B over this plus C over this. And we know the values of A and B and C. So here they are. Now, these are like ratios. So I put the negative 2 down here. I put a minus here. So that's negative 2. And I put the 3 at the bottom so make it a little nice. Okay, and I kept the negative 1/6 at the top. Okay, now to find y or y of t, we have to do inverse Laplace of this. Now, inverse Laplace of this is just negative 1 over 6 times 1 over s. And inverse Laplace of 1 over s is 1, right? Did I erase it? Yeah, it was here. Okay. So you just get negative 1/6. Don't get scared of this. So this and this and this and this is just a constant. This piece here can come out with its minus sign. So you end up with 1 over s plus 2. And inverse Laplace of s plus 2, inverse Laplace of 1 over s plus 2 is e to the negative 2t, right? Let me see if I can remember. We had Laplace of e to the at is 1 over s minus a. Isn't that true? So in this case, a is negative 2. So that's why I got e to negative 2. And the last one, of course, this constant here times inverse Laplace of 1 over s plus 3, which is, by this rule, it's e to the negative 3t, and the constant remains. And that should end the story. Could you have guessed this solution? I think you'll have to be more than a genius. I remember not long ago, we started with things like this. Solve for y. Yeah. Now, and everybody can guess the answer, of course. Now, if somebody gives you this and say, solve for y, this is out of t. There is no way you would guess this one. And it looks ugly. Okay. Let me put parentheses here. Yep. Okay. And that should end this video. I hope it wasn't too confusing. Kind of straightforward, so long you follow the proper steps. And I will assign you some homework on Canvas. Have a good one.